Good morning, everyone. So far we have been discussing about semiconductor materials. We are discussing about the band structure, the energy band diagram. Then what about the intrinsic in intrinsic semiconductor? What is the carrier concentration? We discuss about extrinsic semiconductor, how the doping helps to modulate the carrier concentration as well as the conductivity of the material. Then we look at, okay, so what are the different generation and recombination mechanisms? All right. How electron hole pairs are generated, how they are recombined. There are various mechanisms. Then we looked at, okay, what happens to the electrons and holes. Okay, if you create an excess amount of the electrons and holes, what happens? We saw there are two predominant transport mechanisms. One is the drift, other is the diffusion. Right. So we know all these different things. Okay, now what we are going to do is that we are going to, if you want to understand, okay, if you want to know how the semiconductor device or the system, okay, so how does it evolve spatially? Okay, the spatially, how does a carrier concentration evolve spatially or temporally? We need to put all these things into one place, okay, and create something known as the equations of state. So equations of state, okay, these are the basic equations for semiconductor. Okay, this is very similar to maybe like a Maxwell's equations in electromagnetism, right? So these are, okay, some maybe we will see later. Okay, one of these equations is shared even with the Maxwell's equation, but we call this as equations of state. So in order to understand the operation of semiconductor devices, what we typically do is that we solve these equations in semiconductor devices under some boundary conditions and under some conditions, right? Whether the bias and all those things. Now let us see. Okay, so here is the big picture. Okay, so as I mentioned, we discussed this one. We discussed the carrier concentration. We are doing, okay. So this is the last part. What happens when you apply a perturbation to a semiconductor? Essentially, when you shine light or apply voltage. So after that, okay, we can start about semiconductor devices, right? So all these are required. Okay, so these are we are building up. Okay, so you have to have a strong foundation. Okay, so these are the foundational knowledge which is essential in order to appreciate and in order to understand semiconductor devices. So let's go back to the reservoir analogy. Okay, we have seen this earlier. So okay, we can think about the semiconductor device like a reservoir, right? So all we are accounting for, okay, we are doing some kind of a bookkeeping. Okay, so a reservoir, a civil engineer may be interested in, okay, so what is about the water level in a reservoir or a dam. Okay, so the water level depends upon the inflow minus outflow plus whatever the precipitation minus evaporation. So you can put the same picture, okay, you can put the same analogy for a semiconductor device, right? So instead of here in precipitation, we may be talking about generation. Evaporation means, okay, loss of water. Okay, so here how do they lose? Okay, that is about by recombination. So in the case of semiconductors, we have seen that the flow could be due to drift or diffusion of carriers, right? So there could be a third transport mechanism. We visited this briefly. This is known as tunneling. Okay, but the tunneling, okay, we will see later. Okay, when we require incorporate tunneling as a transport mechanism. So let us now to think about drift and diffusion only. Alright, so the first thing what we are going to write is something known as a continuity equation. Okay, so continuity equation is same. Okay, the same thing. Okay, so instead of water, okay, what we are going to write? Okay, so in this case, okay, we are writing the continuity equation for holes. Okay, so that is, you take a small volume inside a semiconductor. Okay, so this small volume, so this thickness is delta x, right? The area of cross section is A. Then the volume of this material is A delta x, right? The volume of this differential element. So what we are going to write is, we have this equation, that is a rate of increase in hole concentration. So what we are doing is that we are tracking the change in the hole concentration in this differential volume. So it is very simple. All you need to do is this bookkeeping. Okay, you see what is the net inflow. Net inflow means what is the inflow minus outflow. That is the net inflow, plus generation, or how many holes are generated, minus how many holes are recombined. Okay, that is it's a very simple expression. So what we are going to do is that, okay, so the rate of change of so this is the hole concentration, that is a P. P multiplied by the volume, the differential volume, that will give you the total number of holes, right, in that volume. So, that is, then dou by dou t is a rate of change in the hole constant, the rate of change of the number of holes. Then what is that one? That is equal to, okay, so suppose there is a current, there is a hole current coming here, okay. So, this hole current, okay, so this hole current at this point minus the hole current at the other side, okay. So, that is this one, that you divide by Q, that will give you the number of holes, okay, multiplied by the area, okay. So, this is the current density, the change in current density multiplied by area, that will give you the net inflow of the holes, okay. So, this is the net inflow. Net inflow means, okay, it's a the inflow, the flow in minus flow out. All right. What else we need? Okay, that is the generation recombination. Okay, here also we have the generation rate per unit volume, right, and the recombination rate per unit volume. So, you multiply that also with the differential volume A delta x, right. So, if you see here, okay, so what you can do is here, so what I am doing is that, okay, I am going to divide the all quantities by A delta x, right. So, what happens, okay, so this becomes dou p by dou t. So, in this one, okay, it is Jp, okay, so A delta x, okay, so that means, okay, there is an delta x coming in the denominator minus Gp by Rp. If you look at this term, okay, okay, so this is nothing but, okay, this is how you define the derivative operator, okay, this, okay, if you recall this one, okay, so this derivative operator is nothing but, okay, d times Jp by dx, alright, so this one. Alright, so this one is in the one dimensional case, when you have only x, okay, this is nothing but d minus d. On the other hand, okay, if you are tracking in all three dimensions, okay, essentially you will have d by dx of jpx, okay, plus d by dy like this one, okay, that term will be there. You might have seen this term, okay, this is nothing but the divergence, okay. So I can write this thing in a general, okay, so that is dou p by dou t is equal to minus of del dot Jp, okay. So, this is, okay, in a single, so this minus sign is coming here, this is minus sign, alright, then minus generation minus recombination, alright. You may wonder why this minus sign is here, that is because the divergence means, okay, so we are tracking net inflow, okay, so divergence actually is net outflow, okay, so that is why there is a negative sign here, okay. So, the del dot something, okay, so del dot some, for example, this is the net outflow. Okay, but here we are interested in the build-up of the holes in this volume. Okay, so that is why you require a negative sign, that gives you the net inflow. I hope this is clear. So, you can write a similar expression for electrons also. Okay, so this is actually known as a continuity equation, right. So, continuity equation you have seen, you write many places. Okay, essentially we require a continuity equation where we are doing some bookkeeping or accounting for the number of particles. Okay, so you might have done this in fluid mechanics or other thing. Okay, where there is a mass transfer, right. So, you see continuity equations in different areas of physics and chemistry. Now, let us come to, okay, so having learned about the continuity equation, let us formally see what constitutes the equations of state, right. So, first one is the, okay, let us start with this one, okay, this is the continuity equation for holes. This is the continuity equation for electrons. The only difference is that, okay, the electrons has a minus q, okay, so that is why this minus has become positive here, right. Then what you have is you have the electron current expression, current density. This is the drift current and this is the diffusion current. Similarly, there is a hole, okay, this is a drift current and there is a hole diffusion current, right. And the last one, okay, last one is actually, okay, so this is nothing but the Gauss's law, okay, del dot D is equal to rho, right. This is, okay, so this is already a part of a Maxwell's equation. So, we are using that one. So, because we need this one, right. So, because, okay, if you have any volume distribution of charge, okay, how that is related to the electric field, right. So, if you look at these equations, okay, these equations are also known as Shockley's equations, okay. So, okay, just like Maxwell didn't create all the 4 equations, okay, so it was not Shockley who created all these 5 or 6 equations, but Shockley used this one, okay. For example, we will see later when he came up with this idea of a junction, PN junction or junction transistor. Essentially, he solved these equations, okay, in order to derive the current voltage expressions of a PN junction diode or a bipolar junction transistor. Okay, so that is in his honor. Okay, we are calling them as Shockley's equations. Okay, so for example, the Maxwell's equations also has the same thing. Okay, del dot D. Okay, divergence of this one. So there is some commonality between the Maxwell's equations and this set of Shockley's equations. So if you look at these equations, okay, let us pause for a minute. So these are actually coupled equations. Okay, why are we calling coupled? Okay, because for example, if you look at the J expression here, okay, so this J is coming here. Okay, so if you want to solve this equation, so typically we want to know, we would like to know everything on the right hand side of the equation so that you can find the left hand side. Okay, so you should know what is Jn here. Okay, so Jn. But if you want to know Jn, okay, you need to solve, okay, for these ones. Okay, in order to calculate Jn, okay, you require the, okay, let's assume the mobilities are all constant. Okay, so that you require n as well as electric field as well as the gradient in the electron concentration, right? So you require n, you require electric field, you require the concentration gradient. But where will you get n electric field and this one? Okay, for that again you need, okay, so in order to get, okay, you need to look at this equation. Okay, so this equation, so this n, okay, if you know the concentration, you can get electric field. Okay, so D is equal to epsilon E. All right, so but the problem is this n, okay, is actually coming from the left hand side of this equation, right? So in order to have, okay, so you need, actually you are trying to solve n here, but you require that n here. So that is why these are called coupled equations. Okay, these are coupled. Okay, so you cannot just solve one at a time like this one, right? So you need to solve all of them simultaneously. Okay, so that is why they are called coupled equations. And also these are differential equations. Okay, coupled differential equations. Okay, we will see later, depending upon the conditions, whether it could be a first order differential equation or it could be a second order differential equation. But in a real device, okay, so the real device, it becomes very complex. Okay, so for example, your doping concentration, okay, the doping concentration here, okay, doping concentration could be varying with time. Your generation and recombination events could be varying with time as well as in space, right? Sorry, so doping concentrations will be varying with space. Okay, so I'm sorry, this one. So that is why in a real device, okay, real device, it becomes very difficult. Now there are two methods to solve these differential equations. Okay, this set of equations. Okay, one is known as numerical. Okay, so that is, okay, essentially you might have studied about various numerical methods, right? Okay, so you discretize the differential equations and then in a small volume or a small, whether it's a one dimensional or two dimensional or three dimensional, you can solve for all these variables. Okay, so it gives you a detailed solution. Okay, detailed solution, and you can it's not like you will see the result of only n and p. You can see any parameter, for example, field, electrostatic potential, current, everything you can find at any point in space as a function of time, right? So it can apply to a structure. But for that, okay, you either you should write your own code, okay, your own code to solve these equations, or there are which are something known as device simulators. Okay, device simulators are there which solves these equations, okay, for any device geometry. On the other hand, but I think the thing is that, okay, so you solve this these equations on a device structure, you get some results. But you may get some numbers or something. But in order to make some sense of this one, okay, you should know somehow how the solutions looks like. Okay, for some cases, that is where the importance of analytical solutions are important. Okay, so analytical solutions, just like we saw in the case of Schrodinger equation. Okay, you are not able to solve Schrodinger equation. You are able to solve Schrodinger equation in a closed form for only some cases. But that gives you the insight. Okay, what could the solutions look like, right? So it gives you a lot of insight, okay, when if you can solve a system analytically, right? So that is very important. Okay, so if you have some insight, okay, then you can appreciate, you can check whether the output of a numerical solution is correct, or whether you have made any mistake or this thing. Because if you do some simulations, okay, if the convergences are okay or something, you get some numbers. Okay, yeah, but the purpose of the computation, as I think Richard Hamming mentioned, it's you have to get insight, okay, not to get a handful of numbers, right? So that is this one. Okay, so here what we are going to do is that, okay, in this course we are trying to solve these equations analytically for some cases. I also want to mention one more thing. Okay, so there is actually 1, 2, 1, 2, 3, 4, 5. There is a sixth equation also there. Okay, that is to keep track of the traps. Okay, so as we discussed about the Shockley-Rideau, okay, Shockley-Rideau mechanism. Okay, so we need to keep account of the traps also. Okay, so how the traps they are populated, whether depopulated, there is a emission, this one also there. So because that will get coupled into one of these recombination, this one also. So you have to write a separate the continuity equation for the trap states also. Alright, so now what we are going to do is, okay, as I mentioned, okay, these are coupled differential equations, alright, and it depends upon the boundary conditions and whether it's a two-dimensional system, one-dimensional system, it could become very complex. So what we are going to do is that we are trying to solve these equations. Okay, first thing is we are going to do it for a one-dimensional semiconductor. Okay, so one dimension. So okay, so you don't need to worry about the divergence. Okay, you can convert everything into d by dx. Then other thing is that, okay, we will try to do it in a uniformly doped semiconductor, alright. So that is, there is no gradient in the doping, right? So that means, okay, all the dn by dx, okay, you can, okay, so dn by dx, okay, this is nothing but, okay, dn n0 plus delta n, okay. So if there is any change in the excess carriers, you can do this one, but the dn0 by dx is flat. So you need to worry only about how does the excess carrier concentration varies over distance. The last assumption what we are going to do is something known as a low level injection. Okay, so do you remember what is low level of injection? That is the delta n and delta p, okay, is much less than the majority carrier concentration, but the delta n and delta p is much greater than the minority carrier concentration, right? So in such cases we saw that the net recombination rate, you can write as whatever the excess carrier concentration divided by the minority carrier lifetime, right? So we are going to use this one here. Okay, we are going to assume it's a low level of injection. So if you do that, okay, so you can, what you can do is that, okay, once you have this one, okay, so you can put this the current expression into the continuity equation there, right? And then if you assume a uniformly doped case, okay, essentially you can get one single equation for electrons and one single equation for holes here, right? So that is essentially you are putting the continuity equation and you are putting the current, right, current in the continuity equation. So you get one differential equation. You can see this is a second order differential equation, right? And the unknowns are the excess carrier concentration. For example, this is the excess electron concentration in a p-type semiconductor. So this excess hole concentration in a p-type semiconductor. So since we are tracking about electron concentration, this is the diffusivity of diffusion coefficient of electrons. So this is the mobility of electrons, and this is the excess electrons, and this is the minority carrier electron lifetime. Okay, electron lifetime in p-type material. And this is the any other generation. Okay, so if you have an external generation or something, that is this one, right? So this is the external generation. Okay, so this is all about the internal minus the generation minus recombination, that is this one. Similarly, these are for holes. Okay, so this is for the holes. Okay, if you have the holes, okay, this is the diffusion coefficient of holes. All right, so this is the mobility of the holes. This is the whatever the electric field which is present, right? And this is the external generation. All right, so we need, okay, so these are the drift diffusion equations, these are the transport equations, and with that, okay, you require if you want, you require the rho, that is the space charge. Okay, so if you have this one, so this is the what we call as a Poisson's equation or something. Okay, so if you can solve the one transport equation and one Poisson equation, that is why you can solve for it. It will give you the complete detail. So that is what, as I mentioned, the numerical similarities does. Then what? Okay, so other assumption is suppose we assume that, okay, so let's assume, okay, let's make it much more simple. If we assume there is no applied or internal electric field. All right. So for example, if it's a uniformly doped semiconductor, we are not applying any bias, there is no internal electric field, okay, then electric field goes to 0. then it becomes the equation becomes even simpler. Okay, so that this term is gone, this entire term is gone, right. So then you are making it much more simpler. So now you can see, okay, these differential equations are something which you have seen before, right. I think these are something very familiar, it looks very familiar, right. So then other thing we need to understand is that, okay, so in a semiconductor, okay, so far we have been discussing about some things happening at the deep inside the bulk of a semiconductor. But if you are interested in a semiconductor device, okay, so the semiconductor device will always have some surfaces or interfaces. All right. So let's assume there is still only one material. Okay, so there are no interfaces between materials. Okay, but there is still a surface, right? So now the question is, how do you, what has to be done? Okay, because in order to solve a differential equation, you need to do something known as the boundary conditions. Okay, so there is some boundary at the surface. Okay, so how do you treat the surface? Okay, so there are two types of surfaces. Okay, one is actually known as a free surface. Okay, the free surface is that, suppose this is a body here. Okay, so you have a free surface here. Okay, so this is the boundary region of a semiconductor that is actually not electrically connected to anything else. Okay, so this is, for example, this is a semiconductor body or something like this one. I can say that this top surface, okay, it's actually a free surface. Okay, it's not electrically connected. If suppose it's a single block, okay, so now that means, okay, it could be like, if you suppose this is sitting in a vacuum or something, then every surface is like this one. Okay, it could be a free surface depending upon the other condition. So that means, okay, so the normal to the surface, the current which is normal to the surface should be equal to 0. All right. So the total current which is going inside, it should be equal to 0. Now, so other thing is that, okay, so sometimes at this surface, okay, there could be a net generation or recombination happening. Okay, so we will see later, okay, how can there be a recombination? Okay, that depends. Okay, so how can there be a net generation or recombination? Okay, let us assume that if there is some generation or recombination happening here, that means, okay, there must be a flow of carriers into and out. Okay, into and out, that is happening, but the total current, okay, the total current at the surface is still 0. Okay, the total current is, but the whole and electron component, they are separately not. Okay, so that means, okay, the net generation at the surface equal to the electron current by Q or minus hole current by Q. Okay, so that makes the total current. The total current is still 0. Alright, so this is about a free surface, right? The free surface. On the other hand, there is another kind of a surface which you are interested, that is actually known as an ohmic contact, right? Suppose you may want to connect. Okay, so for example, this is how you connect a semiconductor device to an external world, right? So you require an electrical connection, right? So electrical connection to the semiconductor to the external world. So actually, an ideal ohmic contact, okay, an ideal ohmic contact is something which has some, okay, so we will see this term, okay, which is actually known as a infinite surface recombination velocity. Infinite, okay. So what does it means is that, okay, so whatever the excess carrier concentration at that point, okay, whether it is delta N or delta P, there goes to 0. Okay, so that this happens in an ideal ohmic contact. Okay, we will see later, we will see when we discuss about metal semiconductor junctions, okay, how do you realize an ohmic contact? Okay, that we will discuss later. But an ideal ohmic contact, this is a condition, any excess carrier concentration, it goes to 0, and the carrier concentrations are the equilibrium concentrations. Okay, so that is why. And the other thing is that we use ohmic contact to transfer current. Okay, so then the current is flowing through the ohmic contact. Okay, so that means the current should be equal to whatever. Suppose there are hole and electron current are both there, so it's the sum of both hole and electron current. And this you can write in terms of the flux also, because the current directions and flux current directions are opposite. Okay, so you can write like this one. So in this also, in a general case, okay, at this contact also there could be a net generation recombination, right? So in an ideal, if there is no generation, if there is no net generation or recombination, whatever this excess current, right? What is this current? This is entirely supported by majority carrier current, right? Whether it's so if you make an ohmic contact to an n-type material, okay, so whatever the current comes, okay, inside the semiconductor, it becomes an electron current. suppose you are making a ohmic conduct to a p-type material. Okay, so whatever the currents here comes here inside the material, it becomes the Hall current. On the other hand, okay, if there is some generation or recombination events are happening at an ohmic contact, there could be a minority current also. So, for example, this is a case, okay, this is a case where there is no recombination. So, whatever this current comes here, this is an n-type semiconductor. Okay, so in order to support this current, okay, there could be electrons going in this direction. Okay, then only there will be current continuity at the ohmic contact. So, this entire thing, okay, so this one, okay, so in this case it becomes Q into A into F of ES, right, is equal to I, right. So, minus Q, okay, minus Q, that is the electron current. So, on the other hand, if there is some recombination or generation happening here, for example, if it is an n-type, okay, there could be a Hall flux, okay, a Hall flux also there, that is to support the generation and recombination. Alright, so the direction of the Hall current, okay, it could be because you require the electrons to go in this direction, that is because in order to support this current. Okay, so the direction of the Hall current, it depends upon whether there is a net recombination or net generation. Now, let us take some special cases, okay, and we will try to solve this drift diffusion equation. The first thing is that it is a very simple case, okay, that is actually you have a semiconductor here, okay, it is an acceptor doped, okay, acceptor doped means, okay, it is a p-type semiconductor, okay, it is a p-type semiconductor. Then it is a thin piece of semiconductor and you are illuminating that semiconductor everywhere. Okay, so that means there is no difference between whether it is outside, inside, something like that. Okay, everywhere there is generation of electrons and Hall pairs are happening, right. So, then, okay, in this case, okay, it's a p-type semiconductor. Okay, then we are interested in, okay, we are still doing low level injection. Okay, so then we need to track only which are the minority carriers? Those are electrons in a p-type. Okay, so that is why we are writing only this equation for excess electrons. What about the holes? What about the holes? Because this is a low level of injection, okay, the Hall concentration is still the majority carrier concentration. So, we write, so there is no internal electric field because this is uniformly doped semiconductor and we are not applying any external field. Okay, so there is no electric field term here. So, this is a diffusion term, this is a recombination term, this is a net generation term from the out. So, if you try to solve this one, okay, so what happens is that, okay, so then what you can neglect this term. Why? Because it is uniformly doped everywhere. So, there cannot be any concentration gradient because it is every point of the semiconductor is being illuminated. So, that means, okay, you have only these terms, right. And for example, then if suppose you are turning on the light, so this is actually the variable t. Okay, we are trying to solve both as x as well as t. So, if you at t is equal to 0, there was no excess electrons, okay, that was equal to 0. But if you wait till infinity, that is if you wait for a long time, what happens? Okay, this reaches a steady state condition. Okay, this reaches a steady state condition. Then how do you calculate the steady state value? This we have done earlier. Okay, so you put this equal to 0. In steady state, okay, this term, okay, whatever the transient, it has died down. So, what is this one? Okay, so then only you are left with only these two terms. That means, okay, delta n x at t tends to infinity is actually nothing but Gn times tau n. Alright, so this is very similar to your RC charging. Okay, so we did this problem in the I think in one of the previous classes. So, we can solve this differential equation. The differential equation has a very simple. So, this is the value at infinity, okay, as infinity and 0. Okay, so this is very similar to your RC charging expression. Okay, 1 minus exponential t by tau n. So, you can see it increases and it finally reaches a steady state value, which is nothing but Gn times tau n. Okay, Gn times tau n. And this is the time, okay, as the number of lifetimes. Okay, so we know, right, okay, maybe at least you require only five time constants to reach almost like a 99.5% like this one, right. So, this is what this is, okay. So, there is nothing, okay. So, if you already know how does the first order differential equation to solve, okay. So, you may have done this many times in your +2, for example, RC circuits, RL circuits and all those things, okay, it is very similar. Let us now make it slowly increase the complexity of the problem. So, what we are going to do is that, okay, so here you have a bar here, but we are illuminating only the bar from only one side. Okay, let's try to understand the problem qualitatively. So, what happens when light is incident on it? Okay, it will create lots of electron hole pairs at this edge, right? So, then what will happen? Okay, so there is no electric field. Okay, this is still uniformly doped. What will happen? There is a law. You can see there is a concentration gradient is here. So, the concentration gradient, okay, this whatever the electron hole pairs here, okay, so this is still under low level of injection. Alright, so this is a p-type material. So, these electrons, okay, it will try to diffuse because there is a large concentration gradient. Okay, so here it may be at the it will try to diffuse. Now, let us see this one. Alright, so other thing is that, okay, there are no traps here. Okay, there are no traps. Okay, so there are not traps means what will happen? There is no recombination. Right. So, you may be wondering what happens to these electrons. Okay, let us see let us see. So, what are the boundary conditions? Okay, suppose this is the length of the this one is B. Okay, if this is B, and suppose you have an ohmic contact here. Okay, this is an ohmic contact. Okay, ohmic contact here. So, then what we have seen ohmic contact. Okay, so the excess, what are the minority carrier concentration? It should go to 0. Okay, it should go to 0. Right. So, when it reaches steady state, okay, so all you have is, okay, this equation, this is equal to 0. Okay, so a second order differential equation, it goes to 0. All right. So, if it's a second derivative 0, that means, okay, that function should be linear. It's in first order, right? In linear. So, essentially what you get is whatever this concentration here, okay, it decays linearly, okay, and it goes to 0 at the other end, right? So, this is what happens, right? Okay, so let us look at this one. So, you can see the electrons are flowing like this one. Is there a current in this device? Is there a current? Yes, because if you take the electrons are flowing in this direction, that means, okay, so the electrons are moving in this direction. So, the electrons are moving, okay, so there could be a current in the other direction. Okay, so there could be a current happening inside this device. Is that clear? So, now let us make it little more complicated, that is by adding some traps. Alright, so here you have traps here. Okay, so here you are introducing some traps. Okay, so in earlier case the electrons were not recombining. Okay, so electrons were not recombining because of these boundary conditions. Okay, because these boundary conditions, you may be wondering why the electron concentration is reducing. Okay, that is because, okay, that is to satisfy this boundary condition. Okay, so you have large number of electrons here. Here the electron concentration goes to 0 because you have an ohmic contact at that point. And in this case, okay, so this electron, if there are traps here, okay, electrons will undergo recombination in its journey to the right hand side, right. So, here also what you can say, there is no generation inside this device, all the generation is happening at this boundary. So, what you can do, okay, when it reaches steady state, again you can put left is equal to 0. So, you have only these two terms, okay, these two terms, right. So, this is also, it is like a second order differential equation, right. So, the solution, okay, so what I am doing is that, okay, so you can write this differential equation like, okay, so dou square delta n by delta square minus delta n tau p by dn tau p. Okay, so the dn tau p, okay, I can write the dn tau p is equal to ln square. Okay, so I am calling this parameter as diffusion length. So, if you look at the solution, okay, so you have solved this kind of differential equation many times. Okay, one is a growing exponential, other is a decaying exponential. Then you apply the boundary conditions to find what is A and B, right. So, here also at the end, okay, for example, if you have an ohmic contact, okay, you can make delta n or x b equal to 0. Okay, that is an ohmic contact. So, then what happens, okay, if you have an ohmic contact at the other end, okay, you solve for this, you have this one. Okay, essentially what happens is that, okay, you can solve the solution. Okay, you will get a solution something like this one. So, this one important parameter is ln. Okay, ln is known as the diffusion length. So, diffusion length is the average distance. Okay, in this case it is a diffusion length of electrons in a p-type semiconductor. That is the average distance an electron diffuses before it gets recombined, right. So, this is a statistical parameter. It is not like if you observe one electron, you will see it recombine. Okay, it's an average distance the electron travels inside the semiconductor, okay, before it gets recombined. Okay, remember, this is not, okay, there is no internal electric field. All right, so if there is an internal electric field, okay, so that will affect the transport of the electron. Okay, so depending upon whether the field is opposing or aiding the electron, right? Now, okay, so those are the cases. Okay, let's take one more case. Okay, this is a very famous experiment. Okay, so this is actually known as Haynes-Shockley experiment, right? So Haynes-Shockley experiment. Okay, so we are adding one more complexity, that is we are applying a voltage. Okay, that means, okay, you need to retain the term which has the electric field. So essentially, it is the same thing. Okay, so you have a body of semiconductor and you are applying a field inside the semiconductor, and rather than using light, okay, we are injecting the excess carriers electrically. Okay, so you have an emitter here. Okay, so using some pulse, we are injecting minority carriers here. Remember, it is still under low level of injection. So it's a p-type substrate. So we are injecting electrons here. So what we are interested in, okay, we are interested in what happens to that group of electrons, okay, which are getting injected. What will happen? Okay, right? So we start with the differential equation here. Then, okay, so this is I'm giving the solution here, right? I think this is a differential equation also you might have done earlier also, but this comes in. For example, if you have done some other problems, okay, you may have. So this expression, it has got a Gaussian function. Okay, so this one, okay, so you might have studied Gaussian in probability or statistics. Okay, so that is why it looks very similar. So if you look at the solution, okay, it will look like something like this one. Okay, suppose you inject a pulse here. Okay, so that pulse here. So that pulse, if you observe the pulse, for example, okay, you are observing the pulse at essentially you are looking for current here, and you are looking at the voltage, right? If in the absence of electric field, okay, if the electric field is zero, what will happen? What will happen is, suppose you pulse here, so this electrons will diffuse. Okay, it will try to diffuse, and the excess carrier concentration, it keeps on reducing. Okay, it keeps on reducing, and it goes to zero. Okay, it diffuses and it also undergoes recombination. There are two things happening here. There is a diffusion of electrons and there is a recombination of electrons, are both happening. On the other hand, if there is an electric field is present, okay, if there is an electric field is present, what will happen is that, so these pulses, okay, if this pulses, okay, it will try to flow, because these electrons, okay, you are applying a negative field, so it will push these electrons to this side. Okay, so that is why you can see this pulse is traveling. Okay, while the pulse is traveling, it is traveling under the influence of electric field, and also it is traveling under the influence of diffusion. But on the other hand, okay, these electrons, okay, it will undergo recombination also, right, because of this step. So that is how this. So you may ask, okay, why this experiment is important? Okay, this is historically important because you can use this experiment to calculate several things. Okay, one is minority carrier mobility. So in this case, what is the mobility of electrons in a p-type material, that you can get, and you can find the lifetime. Okay, so the lifetime is here, and you can get the diffusion coefficient and all those things. Okay, so that is why this is a very important scientific experiment, all right, which uses if you know the drift diffusion equation, you can solve and you can find valuable material parameters, okay, or like the lifetime of the minority carrier lifetime, the mobility, the diffusion coefficient, and all those things. All right, I hope this is clear. So the next example we are talking about is actually known as surface recombination. So in the case of surface and the ohmic contacts, we discussed about the surface recombination. All right, so there I mentioned about there could be a net generation or recombination even happening here. Okay, but you may be wondering, okay, why there is a additional, okay, why there is an additional recombination happening at the surface. Okay, the reason is that, okay, so we have this energy band diagram. Okay, so in the energy band diagram in the semiconductor, we have mentioned that, okay, so inside the semiconductor, okay, there are no energy states available for the electrons, right? So that is true in the case of somewhere deep inside the bulk of the semiconductor. When you come to the surface or any interface, what happens is that So, okay, you can see this crystalline, the silicon crystal. Okay, so every silicon atom is bonded with the four other silicon atoms. But when it comes to the surface, what happens is that, okay, so the topmost atom, okay, if you look at the topmost atom, okay, so it may be bonded with only 2 or 3 atoms. Okay, so that is very difficult, because these bonds are dangling. Okay, that is, they are left behind. Okay, so there is no proper termination of these bonds. Okay, such bonds are known as dangling bonds, right? So, if you try to calculate the band structure of the silicon lattice at the surface, because in the presence of dangling bonds, what you will get is that, okay, so there you will see surface state. Okay, there will be states inside the energy band gap. Okay, inside the energy band gap. So, this energy band gap, okay, so what happens is that, okay, so that means, okay, these energy band gaps, it can capture an electron from the conduction band, it can capture a hole from the valence band, all these things will happen. So, what it does is that, okay, it will affect your mobility, it will affect your the drive current, all those things, right. So, these are very important. Okay, so whenever there are surfaces or interfaces, okay, you need to do a proper termination, or what we do is something known as a passivation. Okay, you try to terminate these dangling bonds typically with a hydrogen atom or some other atom, maybe an isotope of a hydrogen, for example, deuterium and all those things. We passivate that dangling bonds. So that is to reduce the number of interface states. Okay, these are known as interface states. Okay, these are states in the energy band gap which are created due to the dangling bonds at the interface between silicon and some other material, or at the surface of the silicon. So, this is actually very important. Again, this is actually very important historically. Okay, so the proper appreciation of surface states and what can be done to control the surface states. For example, if you look at the entire semiconductor history, okay, the semiconductor history, you look at the semiconductor devices, ICs, design and everything, right. So, there is one pattern which is considered as the most important pattern in the IC history, right. So, this is actually known as the invention of the planar process by John Herney. Okay, so Herney was an engineer. Okay, he was somebody with a double PhD in physics. Then he was recruited by William Shockley to work. Then he moved on to the Fairchild Semiconductor. So then he came up with this idea of planar process in 1959. So we have to look at till then. Okay, there used to be bipolar junction transistors. There is an emitter, there is a base, there is a collector terminal. So they used to make this transistors, okay, which is known as a mesa structure. Okay, the mesa is something like a small plateau. Okay, so that is why. So it looks like a plateau here, right? So the mesa transistor, okay, it had high leakage currents and it had some various reliability issues, right? So what Herney identified was that, okay, because these are all, because you have this, okay, so there is a junction between different materials, there is a surface here, okay, these are all exposed, right? These are exposed. So what Herney come up with the idea was that, okay, you do a proper passivation, that is, you don't leave any exposed areas. Okay, for example, all the exposed areas, they are properly terminated, passivated by silicon dioxide, right. So this improved the performance of the device, it reduced the leakage current, it increased the reliability of this device. Okay, so that is why this is a very important invention. The other important invention is that, okay, it improved the lifetime of the other important thing is that, okay, so you do this one, okay, this is actually known as planar process, the surface is planar. Okay, now you have a silicon dioxide sitting everywhere. Okay, so what you can do is that, okay, suppose you have you can make another transistor here, then you can interconnect these two transistors by just depositing aluminum. Okay, you etch trenches in suppose you etch trenches in this one and you can interconnect this. So you can go from one transistor to many transistors, right. So that is the idea of integrated circuit. Okay, that's the idea of monolithic integrated circuit. So the planar process, that was actually the stepping stone. Okay, without the planar process, okay, we would have stuck with the discrete transistors. Okay, it was not possible to bridge from transistors to integrated circuit. Okay, that is why this idea this is considered as a most valuable pattern, right. So in the case of a surface, okay, what happens is the recombination rate at the surface could be very high if there are lots of defects, right, compared to the bulk. Then what happens if there is a lot of recombination happening at the surface? So what will happen is that, okay, so suppose the carriers will try to diffuse towards the surface, right? So then you can write again the continuity equation here. Okay, this is the dou p by dou t, this is the external this one, and this is a recombination time, and then there is a the diffusion current, right? So you can write like this one. Okay, so you can still write the differential equation like this one. You can try to solve the differential equation again. Okay, so this is in the presence of an external generation. So if you solve this one, okay, it exactly looks like the previous case. Okay, the only thing is that there is an additional GL top A term here. So in the bulk, okay, in the bulk the boundary condition is something like this. So suppose it's the same problem, right? You are illuminating everywhere, but there is a surface here. Okay, there is a surface with an extra lot of recombination. So inside the bulk, okay, so this is the minority carrier concentration, the equilibrium minority carrier concentration. This is the steady state value, okay, the GL and the tau p. But at the surface, the boundary conditions is because there are a lot of minority carriers which are diving into the surface, because there is a lot of recombination is happening. So all you need to do is that, okay, you apply whatever the diffusion comes here, whatever the flux which is coming here, it should be undergoing recombination, right? So this is the amount of holes which are coming. Okay, this is the diffusion flux, the diffusion coefficient multiplied by the gradient of the hole concentration. This is equal to, okay, so what is the delta? That is, okay, what is the hole concentration at the surface minus the whole equilibrium concentration. So this term is actually known as the surface recombination velocity. Okay, so this is a, so because the surface is not a volume, it's a flat surface. Okay, it's a two-dimensional plane. Okay, so we call that as a surface recombination velocity. So the rate of, that is a rate at which, it's a the rate at which the minority carriers are diving into the surface and getting recombined. So if you solve this one, okay, so it's a simple differential equation. Okay, so in the earlier case you had only this one, so you just complicate this one, and you can have, okay, so essentially this is, okay, if you want to plot, okay, the plotting is important, that gives you the visualization. So you can see this is the excess carriers. Okay, this is the excess carriers caused by the illumination. Okay, this term. So towards the surface, okay, this is the minority carrier concentration at equilibrium. So what is happening at the surface is that, okay, there is, because the recombination rates are very different between surface and at the bulk. Okay, so there will be a flux of holes towards the surface, and this is the boundary condition. This boundary condition is defined by what is this S parameter. So you can assume various S parameters. For example, S equal to 0. S equal to 0 means, okay, this term is same. Okay, that is same as this one. That is the case 1, the first problem, uniform illumination. Okay, so you have only this term present. That's a uniform illumination. S equal to infinity. What is S equal to infinity? S equal to infinity, if you put S equal to infinity, you can try to work out, okay, what is this concentration. So this will go all the way to something like this one. Okay, so that is the case like an ohmic contact. Okay, where you have an ohmic contact, where you have infinite surface recombination velocity. That is at this surface, okay, it should go to P0. So you can try to put S equal to infinity here. Okay. So I think that's all I have for today's class. Okay, so we discussed about the equations of state here. So what these different examples will show you is that, okay, how to approach. Okay, so when you apply a perturbation, and you have already, we know all what are the generation recombination terms and what are the transport mechanisms. Then you can put everything as an equation of state. You solve the equation of state, that will give you the spatial and temporal evolution of the minority carrier concentration. So now we are very much equipped to understand the semiconductor devices. So in the next class, we will start with the semiconductor devices, the simplest of the simplest. Okay, historically also it came first. Okay, so that is, okay, it's a diodes. Okay, so we are going to start with the PN junction diodes. Thank you.